Good enough.
Okay, what is happening? I am disheveled. Let me tuck back in here. Okay. End of the day. What is happening? Mr. Nelson here. To finish talking about exponents and radicals. So we've talked about all the exponent laws. We've talked about most of the radical laws. Now it's time to do some problems, the good stuff, the fun stuff. So here we have some of the main laws. There's one more I'm going to add here, but we know that the nth root of a is equal to a over 1 over that n, a to a negative power. A negative exponent always wants to flip to the other side. So
Eric and Sapphire Thistle, your ride is in the student parking lot. Please go there. Eric and Sapphire Thistle to the student parking lot, please.
The ride is there. So with this law, if I had 1 over a to the negative n, I could rewrite this as just a to the n over 1. It just wants the exponent wants to always flip on the other side of the fractional line there. I don't know what that word is. In any case, so that's the reverse side of that. Also, if I had a to the negative 5 over b to the negative 4, I could rewrite this as b to the positive 4 over a to the positive 5. Another thing I can do is if I have a over b to the negative 2, I can rewrite this as b over a to the positive 2. Because this is the same as a negative 2, b negative 2, and then they can switch up and we can take out the square there. That's that. And then a to the power of m, all to the power of n is the same as multiplying the exponents. If we're multiplying two numbers with the same base but different exponents, or just exponents, we can add the exponents as long as the base is the same. And the same thing here. If we have an identical base with exponents, we can subtract if they're being divided. And then one last one I need to show you is, say I have a squared, b squared to the power of 3. This 3 will actually distribute to each individual number. So then we'll get a 2 times 3, b 2 times 3. So this will be a6, b6. So that's that. So with all these tools in our pocket, we can start solving some problems. So I'm going to start easy and work our way up. So say I had, and so say I say express in exponent form. Okay, so say I had, I'll just do one at a time, okay? So let's say I had the square root of 3 expressed in exponent form. Well, the 3 is my a here, and there's an invisible 2 here, so this becomes this becomes 3 to the power of 1 over 2. My n is 2, my a is 3. Let's say I had the cube root of x to the power of 6. Well, I'm going to use this rule again here, and this will be my a, so I can rewrite this as...
Could you call 310 there, please, Mr. Vargas?
So I get x to the power of 6, and then this brings me to this rule here. So I get x to the power of 6 to the 1 over 3. And then I have to use this law here, where something to the power here, all to the power of something else, is the same as just multiplying these two exponents. So x to the power of 6 times 1/3 gives me x to the power of 6/3. 6 divided by 3 is 2, so this final answer is x squared. Okay? What if I had something like square root of 3 over 5 to the negative 2? Okay? There's multiple ways I could approach this. It doesn't really matter where I start. So one possible way I could start with what's inside here. And I want to make it a positive exponent. So I could say, okay, well that's equal to 5 over 3 to the positive 2. And then I could say, okay, well this is going to be all my a, so it's to the, there's an invisible 2 here, so I could write all this as 5 over 3 squared, this guy, to the power of 1 over 2. And then this 1/2 will multiply with the 2 to give me 5 over 3. 2 times 1/2 is 2 over 2. 2 over 2 is the same as 1, so this just becomes 5 over 3. Okay? I could also, I'll write 5 over 3 here. I could have also started by doing the root first. So if I wanted to start with this rule here, I could say, okay, this is the same as...
Could you call 3100, please, Mr. Vargas?
3 over 5 to the negative 2 to the power of 1/2. So I kept whatever's inside and then I did my root law there. And then I spread this out, so this is the same as 3 over 5 to the negative 2 over 2. Negative 2 over 2 is the same as negative 1, so then this equals 3 over 5 to the negative 1. And then I can spread that out, so it's 3 to the negative 1 over 5 to the negative 1. Exponents don't want to be negative, so they'll flip sides. This will be 5 to the 1, 3 to the 1, 5 over 3. Okay? Let's do one more. Kind of in that. So what if I had the quad root of a to the 4, b to the negative 12, b to the negative 8, a 4. Okay? Again, multiple ways I can deal with this, but I'm going to start inside here, okay? First I'm going to fix what's in there. So I can say, okay, I can collect my like terms. So I have a's here, and they're all being multiplied. So I can say that this is the same as, well, a to the 4 plus 4, I add the exponents because these are all being multiplied, times b to the negative 12 times b to the negative 8. So this will give me the quad root of a to the 8, b to the negative 12, b to the negative 8. I'm not going to kick these guys downstairs yet because I'm not done, so I'm not the final answer yet, so I don't have to do it just yet. Now, I'm going to call this my new a in here. So all of that, a to the 8, b to the negative 12, b to the negative 8, is now to the power 1 over 4, if I use this law here. Now all of these exponents are going to multiply by 1 over 4. So I get, this is the same as a 8 divided by 4, b negative 12 divided by 4. Remember, this 1 over 4 distributes to each variable. And v to the negative 8 over 4. And then if I simplify, this becomes a squared, b to the negative 3, v to 8 divided by 4 is negative 2. And now I'm almost done, so I can kick these guys, the negative exponents, down below. So a squared over b cubed v squared. Okay? Now I could have done this part here first, right? Deal with the root, spread out the root, and then collect like terms as well. It's going to work out the same way. It doesn't really matter what order you go in. So one last example, Ferda. Okay, so let's say I had the square root of x squared, y cubed, z cubed over x4, y, z to the negative 5. All to the power of 4, and all being square rooted. Okay. So this time round, I could work with what's in here, simplify down here, and then do the root. But now I'm going to do the root first, just to show you that you can do it either way. So this all becomes then, if I'm going to do the root first, x squared, y cubed, z cubed, x4, y. When there's no exponent, you just assume it's a 1. Okay, z to the negative 5. Any exponent to the 1 is that number. Any exponent to 0 is always 1. 3 to the power of 0 is 1, x to the power of 0 is 1, y to the power of 0 is 1, and then 3 to the power of 1 is 3, okay? That's how that works. Anything to the power of 0 is always 1. Anything to the power of 1 is whatever it is. I talk fast, I'm sorry, it's just what I do. To the power 4, all to the power 1/2. Now, what I think I'm going to do, now I could work inside here first and then do this, but I'm going to just work this against there right there. Because this is going to do everything inside. So I can do this first. I could also work this all through and then apply the 1/2, but I'm going to apply it right now because it doesn't matter what order. So this becomes x squared, y cubed, z cubed over x4, y1, z negative 5, all to the power of 4 over 2. 4 times 1/2 is 4 over 2, which is the same as x squared, y cubed, z cubed, x4, y1, z negative 5 squared. Now I could distribute this too. If I did that, I'd have to distribute it to every single number in here. Instead, I'm going to bring all these guys up and then I'll apply it. So how do I do that? So now I'm going to use this rule here. So I have x, exponent on the top, 2, minus exponent on the bottom, minus 4. Y, exponent on the top, 3, minus exponent on the bottom, 1. And then z, 3, exponent on the top, minus negative 5, exponent on the bottom. Okay? And then all of this is going to be squared. So then I say, okay, I've got x to the negative 2, y 2, z 8. Negative 5, 8. Squared, that gives me x, so now this 2 distributes into each one of these. So x to the negative 4, y 4, z 16. And then so I have y 4, x negative 4, y 4, z 16. And then I can rewrite this as y to the 4, z 16, all over x to the 4. And if I wanted to get fancy, I could write this as also y, z, 4 over x, all to the 4. And then if I were to distribute this, it'd be y4, 4 times 4 is 16, 1 times 4 is 4. So these are both good answers. So we're able to use all these rules. You'll notice all these rules have no addition signs separating any of the variables. Okay? Because once we start putting addition signs to separate variables like x plus y times, times z6, y, well, no longer can I just assume it's one long multiplication, right? So I can't just go ahead and now add y and y there, because this addition changes everything. What ends up happening is now this x has to multiply by that expression. So I get x times z6y, and then this y would have to multiply by this expression. But I have to put the addition sign there now. So this becomes y, z6, y, which I could write, this whole expression would simplify down to y squared z6. Okay, plus, sorry. But this is what we're going to talk about now in our next section on multiplying binomials and polynomials. We're going to learn about that. So far, if you don't see any additions separating the variables, you're good to just run with these rules. But we'll see where they kind of break down. So thank you for watching.